Hello. How's the sound? No. Okay, good morning. So how's this sound? Is it okay? Awesome. Anyone in Zoom land can hear me? Yay. Okay, thank you. All right, so let's get started. All right, so this week, here we are on the 20th to the 24th. So what we're going to do this week is go over ARM data transfer functions more in detail, like how it goes from memory, main memory to register. So you should look at those, and we'll look at ARM decisions and loops. So we're going to start on some programming a little bit this week in lecture. So last week it was all about the binary to machine code. We're kind of moving on from that and starting programming. Your programming assignment 0 is due on Friday. A lot of you have already done it. But this week on Friday, Nathan, the peer mentor who actually created the all the the instructions and specifics on getting the emulator running. He's going to come on Friday and do the lecture and go over how to get that running. We're also going to look at on Friday the structure of an ARM program. It's a little different than what you've written in C++ or Java. There's a thing called the preamble, and there's different sections, and there's a text section and a data section. You'll go over kind of how all that's set up for you. So then we can start writing our ARM programs. Okay. Questions so far? Okay. So you should look at, if you're looking at the pre-recorded videos, you should look at ARM data transfer and ARM decisions and loops. And we'll go over some problems in class. Okay. So let's move. Okay. So a deformat instruction, which we went over a little bit, but we're going to go over a lot more this week. So ARM format, the deformat, the data sorry. Data transfer is going to be from main memory. So whatever your main memory in your computer is, to this register file or the registers, right? So on your chip is the registers, and there are 32 of them in ARM, and they're each 64 bits wide. Every chip is going to have what's called a register file. We went over it a little bit in the ISAs. So every ISA has registers. In ARM, the only way you can only do arithmetic on logic on registers. You can't get data directly from memory and operate, or directly from main memory and operate on it in ARM. And RISC in general, that's one of the things that makes RISC is that you can only operate on data from registers, and there's 32 of them. Another one of the things that defines an instruction set architecture is how many registers are there and how wide are they. So in ARM, there's 32 and there's 64 bits wide. So we don't really go over that much with different types of memory, like in terms of the hardware, but it's kind of, I don't know if it's linear, but it's definitely, there's a function. The faster the memory is, the more expensive it is. So this is the fastest memory we have, right? The best kind of memory we have, or the fastest, and we put that in the register file. Or the register file is, very fast memory. So what load and store do is get data from main memory to a register so we can operate on it. So load, this is load register. This means unscaled. I wouldn't worry about it. And actually, when we end up programming, unfortunately, the emulator we use, even though it's ARM version 8, it's a little bit different than what's in the book, of course. So when you start programming, I think you can do either one, but you can also do LDR in our emulator, which is load register. I think you can put the U in or not. It's annoying. It makes me, I like doing ARM, but there's parts of it like this that are kind of annoying. Like it's a little bit too squishy. Anyway, so what this says is what's in register X10 is an address. This slide set in Canvas, I'm going to show you where it is real quick because I can. So if you go to modules and you go to the ARM instructions of programming and go down to sample problems, it's ARM. Yeah, it's in there, but I didn't link it yet. But if you go, what's it called? I'm sorry. Actually, maybe I could just do it right now. I know I forgot to. Oh, that might be a little hard. I'm really sorry about that. I forgot to link it. But if you go to sample problems and you find the one that I just loaded in yesterday, you'll find it there. ARM data transfer loops examples. Sorry, it's right here. Modified yesterday, apologies, but there it is. I'll link it into the modules this morning. Sorry about that. I was away for the weekend. I'd like to rewind the weekend as well. Anyway, where were we? Okay, so what load's going to do, there's a register. It's got, so this register X10 has an address in it. We're going to go to the address in memory. well, this is an address. We're gonna add 40 to that address, go there, get that data, and load it into register X9. So we'll see more specifically how this works. So what this is a byte, a number of bytes. Our memory is byte addressable, that's what it's called. So every memory address is the address of a byte, right? And we'll kind of see more how that works coming up. But go to so take this address that's here, add 40 to it, and that's the address to go to in main memory. Go get that. And since it's load register, it's going to be go get 8 bytes, starting with this, that address, and put it into that register. So again, we'll see this in more detail coming up. Store is the opposite. It goes the opposite direction. So what this says is go to the address that's given in register X12. Go to that, and then take the data that's in register X7. So X7 has 64 bits or 8 bytes because the register has 8 bytes in it. Go get that 8 bytes that's in register X7 and put it at the address given in register X12. Okay, so we'll go through this in detail coming right up. And then actually we're kind of, in terms of tests and stuff, we're done with, I know you're sad, but it'll probably be on the final, but going from machine code to assembly, not going to be on the next one. So you're kind of done with that for now. I know it's sad. You're sad. I know. Such a valuable skill. But this is the format for a D format. So you have your 11-bit opcode. This is that offset. It's called DT address, but really it's an offset. So we'll look at that. And then this op is 2 bits, and we don't use it for load or store. It's used for other instructions that we don't study in this class. This is the register number that has the address, and this is the register number that will either get the data or store the data. So now let's look a little more closely at what happens. So here we have an instruction that says load register, and it says, okay, so go to the address that's in register X9, add 0 to it, go to that place in memory, get 8 bytes, because it's load register, and put it into register X11. Okay, so let's see, X9, here's our register file. It's 32 long, but I only put 11 of them here. So here's register X9. Here's the data it has. So this is an address. So like we said, every byte in memory is addressed. And again, our memory addresses are 64 bits long. I think that when we say it's a 64-bit architecture, it's referring to the length of an address. So we could have 2 to the 64 bytes of memory in our main memory that we could address, right? Because our memory address is 64 bits long. I think it's also a 64-bit architecture because our integers and floating points can be 64 bits long. So that's also, we can also have really big numbers. So our registers are 64 bits, our addresses are 64 bits, and our numbers are 64 bits. So that's how we describe a 64-bit architecture. But anyway, so here's our address we're going to. So here's our main memory, just a little bit of main memory. So each byte in main memory is going to have an address. So there's that address, and this is the data that's in there. So that's a byte. So remember that's hex, and remember each hex digit is 4 bits. So 2 hex digits is going to be a byte, right? Yep. Yeah. So really this byte would be A1. So it would be really the byte would be 10100001. That's the byte that's in there. But again, we much prefer hex over binary because it's a little more compact, easier to deal with. So this is the byte that's at memory address 8, blah, blah, blah. And so we're going to get 8 bytes or 8 bytes. And we're going to put it into register 11. Okay. So now this is where we get into what's called big endian and little endian. So I don't know, for me, when I was learning it, it's just a bit of a mind. I don't know, I guess different things confuse different people. It always confused me. But anyway, so what does big endian mean? So what that means is we're putting these 8 bytes into this register. What order do we put these 8 bytes in, right? So big endian means the lowest address, which is this one. So we're taking these 8 bytes. So the 8 bytes starting with this address. And big endian means we're going to put the byte at the lowest address at the big end. So this is when you have an address, when you have this, 32, well, here's a 16-bit number, right? This is what's called the most significant bit would be at the left end, and the least significant bit is at the right end. So this is also, the big end. So this says this byte at the lowest address is going to go at the big end. Okay. So we're going to start. So this is what would result in register X11 with big endian storage. So A1 goes here, then 3.2, then 5B, and so on. Okay. Little endian means the address, the lowest byte address would go at the little end. Okay. So this is what would be an X11 with little endian storage. Okay. Just a way to screw things up, not, I mean, I guess it's, I guess like any engineering endeavor, I feel like computers kind of just, I don't know, grew in whatever the latest engineer decided it would grow without all these, without a lot of rules, So there's been, there isn't a decision on whether things are big endian or little endian. And in fact, in ARM, because it's so squishy, you can do either one. You have to say which one you're doing in your program, but you can do either one. So that's like ever more confusing, right? But anyway, so this is little endian. Okay. So here we're taking, again, how the load register works. Go to the address. So X9 has an address. There it is. That's a register. Add 0 to it. Go to that address in memory. That's here. Get that and the next 7 bytes. So starting with this address, get 8 bytes. Take those 8 bytes and put them into register X11. Yay. So there are different widths you can do. So a word is 4 bytes. Okay. So what load word or store word is going to do is it's the same deal. So store means go to X11 and there's data there, put it at the address found in X9. So X9 still has that 8. So this is still our address. This actually says do an offset of 8 bytes. So we're going to add 8 to that address, and so this is where our word is going to start. We're going to go get, or we're going to put it there. So we're going to, but what word says is go to register X11 and only get the lower 31 bits and go store that in memory. Okay, so that's what store word gets, the lower 31 bits. Right. So that's why you might want to shift, like, so say you wanted the different set of bytes or bits, you would shift it. So anyway, so let's go get those lower 31 bits right here, and we're going to put it at this place, and it says we're doing little endian. So that means we're going to have A1 and then 3, 2, and so on. Okay, go ahead. Oh, it's 32. It's 0 to 31. I'm sorry. You're right. I'm sorry. I had on my mind 0 to 31, right? Bits 0. So yeah, sorry about that. So he said, why am I getting 31 bits? I'm not. I'm getting 32. Sorry. Anyway, so this is what this looks like in memory if we use little endian. If we're doing big endian, so here, this is what the register would look like, you know, that previous one. And then if I'm doing big endian and I do store word, it's still going to be 0 to 31, bits 0 to 31, so 0 to 31. But I'm going to go get this one and put it in the lowest address. So this would be 92. And then 58, and so on. Okay? Great. Little endian, big endian, no problem. So there's also, there's load. So what this is load signed word. So we'll see what signed means. So here we're going to go to X9 plus 8, and that's here. And we're going to get 4 bytes because it's a word. And we're going to put it into X10. So we're going to do, and it says big endian, so it's going to be 92, 58, and so on. What signed word means is take whatever's in bit 31. So this is bit, 0 to 31. Take whatever's in bit 31 and it's called sign extend. So the top 32 bits is going to be whatever that bit 31 is. So 9 in binary is 0, right? So bit 31 is a 1. So that means all these bits are 1s. That's what's called sign extending. And we'll see when we talk about 2's complement, that just means, you extend, so a negative number has a 1 in the most significant bit. So if you want to make something more bits, you just extend the 1, right? So that's called sign extending. The sign is going to be 0 or 1, 1 for negative, 0 for positive. And so sign extending is just making it more bits, but keeping the sign, right? So this is signed word. So what it's going to do is put all 1s, okay? Good. Excellent, easy peasy. Great. You can also load a byte. You can load or store a byte. So that's 1 byte. So at least you don't have to worry about big or little endian with that. So the byte, again, is going to load it into the least significant bits. So the load byte is going to go into bits 0 to 7. There's also a half word. I think that's well, it's H on the end. So that would be half word. That would be 16 bits. So you can load or store 1, 2, 4, or 8 bytes, right? So here's load. So go to the address in X9, add 9, so that's here. Take that and put it into register X1. So we're going to take this and put it here. Okay. And then one more. There's one more. Store byte. We're going to take this, the lowest 8 bits, add 10 to what's in register X9. So that would be here. So we're going to put this there. Okay. Got it? It's all about load and store. So when you are programming, you'll have to do a lot of loads and stores because all the data you want. So when you do something like int I equals 3 in C++, that's making some space in main memory, either the stack or the heap. So this would probably be, if it's a static variable, it would be one place. If it's a local variable, it would be on the stack. That's putting it in main memory. If you want to do anything with that I, you have to load it into a register. So you'll learn that, you'll learn that well when you start writing programs. And we will go over the memory model next week. So where things go in memory, we'll go over next week. Okay, so now, conditional branch. So this says conditional branch on 0. So look at register X9. If it has a 0 in it, branch the instruction named my label. So we'll look at, all you have to do in ARM to give something a label is just write it and put a colon after it. So that's how you label an instruction. And then when you assemble it, your assembler will turn that into the number of instructions you're jumping. And then this is a conditional branch on non-zero. So look at X9. If it's not 0, jump to my label. Okay. All right, so now let's write some code. Yay. So like I said, we're writing little bits of code in class. On Friday, we're going to get a little lesson on how to turn those little bits of code and turn it into something that can actually be compiled and run. So what are all the other details we need to make it into just more than just bits of code or snippets we'll do on Friday. But anyway, let's write some ARM instructions for this. So if x equals 14, add 1 to x. If not, multiply by 2. So let's do this. Okay, so first thing we have to do is we have to get x. X is in memory somewhere. Oh, actually, yeah, so we're assuming actually here, sorry, I'm not even bothering with this part. So if you get a problem on a test, you'll probably get something like this written, right? When you really, right, you'll have to get that x into register X9 from memory. on a test, it's going to say something like, assume that X has already been loaded into register X9. But the first thing we're going to do is get ourselves a 14. So we're going to put the value 14 into register X10. Okay, just so it's there for us. And now, so we have X is in X9 and the value 14 is in X10. We're going to subtract, so this is 14, X11 equals 14 minus X. Okay, so now if X10 does not equal X9, then X11 is not 0. So if X11 is not 0, we're going to jump to the else. So conditional branch on not 0, jump to the else. So it'll go down to here. And this is where what I did to multiply it by 2, I just did a logical shift left by 1 bit. So a logical shift left, if we have a 4-bit number, logical shift left, shift it left 1 bit. So that's equivalent to multiplying it by 2. Okay. So we go to the else. If it does equal 0, we just keep going. And we execute this and where we add 1. And then we want to jump. So this is a unconditional branch. This is just go to that label. Okay. And we want to do that because we don't want to execute the else. So we have to jump out. Okay. So yes, you will be writing spaghetti code for this class. And you will come to appreciate languages. Okay. All right, so now let's go the other way. So let's assume that X22 contains a variable called I. X23 contains a variable called J. X19 contains a variable called X, and X20 contains a variable called Y. Write the C code that corresponds to the following ARM instructions. So first we're going to have X9 equals I minus J. And then jump to else if this is not 0. So this says if, so we're going to have if X equals Y. And then if not, we're going to jump to else. So the else is X equals X minus Y. And this is X equals X plus Y. Okay? Go ahead. So if this is the if X equals Y. So here we have X9 is, oh, if I equals J, sorry. I said, I think you meant I equals J. Sorry about that. All right. See, it would be better for me to just go to the next one where it's correct. I'll learn to do that. Okay? All right, good. Okay, so Another thing that you probably, you've learned in, CS2 or, yeah, I don't know, CS2, maybe Java, or your CS1 class, is that arrays are all together in memory. Certainly you should be talking about that in data structures, right? So when you have an array in memory, you're going to have a base address, and that is the first element, right? And so then each element in your array is next to it in memory, right? So if this is all memory, so these are all, what we're going to assume in this class is each hunk of, or each item in an array is going to be 8 bytes, just to kind of keep it easy, right? So if this is at address, some address, this is address base plus 8, base plus 16, right? So each item in the array can be found by adding 8 bytes to the address, okay? So yeah, I used to have, so I learned C, after I got out of college, right? And I had, I don't know, colleagues that used to see if they could write the most obtuse C code they could. Like, I don't know, it was like a challenge to see if they could write unreadable code. But you could, you can, instead of doing A3 or whatever, you could just find the address and, use your ampersands and stars. It's a challenge, I guess it's something to do, write code that no one will ever be able to read. Anyway. So let's write some code to go with this. So what we're going to do is we have a loop from 0 to n. And we're going to make we have 2 arrays, right? So we have n in x9, the base address for A is in x10, the base address for B is in x11, and the base address for C is in x12. Looks like we're comparing items in A and B, and C is going to be the smaller of the 2. Okay. Right, and I do this. I start making problems, and then I forget to update all the slides. So I change this to less than or equal to in the subsequent slides, but we'll see that. So here we're saying if A is less than or equal to, if the item in A is less than or equal to the item in B, then C is going to be A. All right, so let's start. So first we're going to have, we need a variable called I. We're going to put it in x13. So I set x13 to 0. There's tons of ways to set a register to 0. This is just one of them. And then we're going to set up the loop. So the loop is going to be x14 is going to be n minus I. So as soon as n equals I, x14 will have a 0 in it. So once x14 becomes 0, we'll hit the exit. So now we have like the edges of our loop. Now, within the loop, we're going to set up all of our variables. So we're going to have this thing x15 is going to be I times 8. So that'll just be the byte offset, right? So when I equals 0, the offset is 0. When I equals 1, the offset is 8. When I equals 2, this is just like figuring out where to go, what address to go to get that item. Right, so that's what this is. So this register X15 is going to have the byte offset. Register X13 is going to have I. Okay. Here, I'm going to add that byte offset to X10. And so that is going to be the location in memory where AI is going to be. Okay. Yeah, so I is, so X13 is I. We want X15 to be I times 8. So when you do a logical shift left 3, you're multiplying it by 8. So here, this is 1. If I do a logical shift left 3 bits, it's going to be 1, 0, 0, 0. So it's 3 times it. I mean, it's 8 times it. To get the byte offset. So I'll just put it here. So if we have A0 is at this address, A1 is going to be at that address plus 8, right? So each item in the array is 8 bytes wide. Is it clear now? Yeah. So each, yeah. Okay. Each item in the array is 8 bytes. So to get AI, you need to add I times 8 to the base address. And yeah, I saw this on here, sorry. In ARM, you can call something XZR, which I don't remember what register that is. Maybe it's, I don't remember, 30, I don't remember what it is. There's a register in there that always has 0 in it. Actually, I think it's 31. Yeah, so you could put X31. You can also call it XZR. Okay. Yeah, that's a little jargon. I have to remember to not to explain all the jargon. Anyway, so now what we have, X16 is going to have the location of AI. X17, so this says go to X16, that's an address, and load it into register X17. So X17 is going to contain the value that was in AI. Okay. 16 has the address. 17 has the value. So you're going to understand pointers so well by the time you get out. Maybe you'll understand it better. Well, you'll also understand how dangerous C can be. Right? But hopefully you'll understand that when you're out of here. Lets you do just about anything. All right, so then X19 or X18 is going to have the location of BI, right? So the base address of B is at X11. We add this offset value to it to get the location of BI, and then we load, oops, typo, that should be at 18. I did look at these. That should be an 18, I'll fix that. So X18, go to the address in X18 and put it in X19. And then X20 will have the location of CI. Okay, so now we've just set up all of our addresses and values. Okay, so we have the addresses of AI, BI, and CI, and the values of BI and CI. Now, we're going to figure out which is bigger, AI or BI. And so we did a little bit with this. This is subtract and set flags. This is definitely in the videos, but I don't know if I went over in class. So when you put an S on the end of a R type, it's a set flags, okay? So there's flags, definitely in the videos. So what this does is it compares 17, so the set flags, so subtract and set flags is going to set the flags based on the values of X17 and X19. So remember, X17 has the value of AI and X19 has the value of BI. So this is going to say, set the flags according to X17 and X19. So this says branch if greater than. So if X17 is greater than X19. Okay, that's what this says. Branch to else if X17 is greater than X19. Okay, good. So it says, all right, go here if AI is greater than BI. It depends on the, I mean, they do, but it depends on, so that's in the slides. I can go over them on Wednesday in class. They're definitely in one of the videos. It depends on the instruction. So in a subtract and set flags, it does it based on this. And in fact, I think add and set flags, it does the same thing. So you could do add and set flags, and the flags will be set based on the RN and RM registers. And you're right. One of these should be 19. Another typo. That should be a 19, right? So if B is greater than A, or B is less than A, we're going to come down here and set it to B, which that should be a 19, so another typo. If not, it's going to do CI equals AI. Okay. What does setting a flag mean? So I'll definitely go over setting the flags on Wednesday. It's in, I don't remember which video, but one of the ones that you were to be watching last week. So there's several flags. You can find it in the slides and I'll go over it, but there's 4 flags in ARM. And when you say, when you put an S on the end of an R type, it sets the flags. And so there's 4 of them. Off the top of my head, I don't remember what they're called, but what this says, I mean, they each have a letter. There's like a C and a V, and I don't remember that. One's a greater than bit. I don't remember. What I'll bring the slides on Wednesday, but there's 4 flags, and when you do an S instruction, you set those flags, right? And then this checks the flag. So it says be greater than. So what that means, it actually sets whether this register is bigger than this register, right? But there's a particular flag with a letter that I don't remember what it is. But anyway, that's what setting a flag means. Go ahead. That's coming. You're right. I did look at these, but not well enough. Yeah, we need to add 1 to I. Yeah, but what I need is actually adding one. I have to add one to I somewhere here. So I could actually do it right here. So I don't have to do it twice, but I would do add I x14, 1. Yeah, I have some fixing up to do. Yeah, so I forgot to add 1 to I. That goes in here. All right, and then you branch back to the loop and jump out of the loop when I equals 14. Sorry. Isn't I in 14? You're right. What? Yeah, yeah. Whew. All right, well, we'll fix these up and look at them again. I is in x13, and I forgot to add 1 to it. Couple of problems. Just showing you how fun it is to write in ARM. Anyway, and we should, yeah, right. Anyway, all right, so I'll fix this up and we'll look at it again on Wednesday, and I'll also bring the slides on the flags